Lyman and the BM Energy Research Group in 2017. So I'm excited to talk to you guys about the Uinta Basin, where I was born and raised. So first, I'm going to go over acknowledgements for funding. We have the Utah Legislature, Utah Department of Air Quality, Anatarco Endowment for Student Fellowship, and then the Uinta Basin Mitigation District have generously funded us in this project. So ozone, for those of you who aren't familiar, is formed by two different types of compounds: VOCs, volatile organic compounds, and NOx, which are oxides of nitrogen, plus sunlight, which basically gives the energy for these reactions to occur. Ozone exceedance is normally seen in urban areas with summertime pollution, but for two areas in the world, the Uinta Basin and the Wyoming Green River Basin, we see ozone exceedance over 70 ppb in the wintertime. So that's what our group is studying, specifically Uinta Basin ozone levels in areas of dense oil and gas operation. So as you can see, and I have to move this window. Does that help everybody? I don't know if you guys can see yourselves on my screen. I don't know how to make it go away.
We can see your cursor moving around, Makenzie. Is that what you want us to see? We got your cursor. We can see that.
Okay. Zoom is showing me everybody's video boxes, so I just want to make sure you guys weren't seeing that. I had to move it so I could see my graph. So, okay, so differences in pollution or emissions in the Wasatch Front and then the Uinta Basin are quite different, actually. So the Wasatch Front and Salt Lake County see more of an even mixture of NOx and VOCs, which contributes to forming PM 2.5. Where in the Uinta Basin, we see primarily VOCs in the wintertime, which contribute to ozone exceedance. And this usually occurs during inverted periods that cause cold air to basically trap emissions at the lowest elevations of the Uinta Basin. So the purpose of our study, because of these differences that affect the emissions in the Uinta Basin, our team has really been focusing on collecting data to aid in producing more accurate modeling technology to be used in places like the Uinta Basin and places with similar topography and meteorology. Currently, the photochemical models that we are using were designed for modeling summertime and urban pollution. And the model we use predicts a total amount of organics in the basin, though through the use of an official emission inventory. The model simulations are not accurate in the percentage of total reactive compounds. And because of this, we're looking closely to better understand the ratios of compounds and the relative reactivity in the basin. So if you look at the bottom of the screen at this graph, this was made by a senior researcher on our team named Trey Tran, who works primarily in modeling. She shows the model in the lines and then the observed results in the diamonds and triangles. And the different colors indicate the different sites of vernal and red wash. And as you can see, we have a really pretty decent correlation in the total hydrocarbons, but we see quite a poor correlation between the alkenes and BTEX, or benzenes, toluenes, ethylbenzenes, and xylenes, which are more reactive compounds and more important as ozone precursors. So the most concerning thing we see here is that the model is just not simulating the amount of emissions that we're actually seeing. So it's not going to be accurate for predicting or simulating ozone in our area. So to remedy this, we decided to gather data to improve the inventory for our area specifically, and we made different stations. Measurement stations that we call pods, and we deployed them through the densest areas of the oil and gas fields. So this is a picture here of the Uinta Basin. You can see Roosevelt and Ouray, and then the Green River runs down the middle of the screen. So oil wells are here in blue, and then gas wells are here in green. Compressor stations are in purple, and these basically take high pressure systems and is that right? High pressure, yeah, and low pressure systems and create high pressure systems that can be used to make natural gas for transport, sale, or reuse. And then in the blue squares, we see produced water ponds, which are basically lined pits that hold produced water that may be evaporated or transported to injecting facilities to either be injected into the ground or sold for reuse. And then lastly, the pink dots we see are gas plants, which separate liquids for compressions for preliminary processing for use at compressor stations or for sale. And so these are our pod stations. We made, if you see here on the right in this nice winter Arctic scene, our team spends a lot of time out here in this lovely weather. We made, I think somebody's mic is on. I don't know if anybody else can hear that. But we made 10 MET stations, which had meteorological instrumentation to measure wind speed, direction, ambient temperature, barometric pressure, and relative humidity, into 7 other stations that measured only temperature and humidity. And with these and these metal, these selenite canisters down here, we collected C2 through C10 hydrocarbons and light alcohols. And we placed them down here at the bottom of these MET stations and then the other stations. In addition, we had 2 DNPH cartridges that you can see inside this box to collect. And we deployed these for 6-hour day samples and then also 6-hour night samples. And we analyzed the samples for 73 separate organic compounds. Each station was run by a Raspberry Pi here and software that was developed by Dr. Wee Tran, another senior researcher on our team. He'll be speaking right after me. So if you have questions on the software, save it for him because I'm clueless. The energy for these systems was run by a solar panel, and obviously you can see sometimes sunlight is a little sparse in this area, so we also had some backup batteries here in these black boxes down at the bottom. So some of our data that we saw was very supportive of previous years, and after both the 2019 and 2020 collections, we were able to see that there were much higher concentrations during inversion periods compared to outside of inversion periods. So this top graph here was taken during the 27th of February for a daytime collection. And you can see we have almost 8 times higher organic compounds during this inversion episode in comparison to the 17th of April, which was outside of an inversion episode. And again, for those of you who aren't familiar with inversions, these occur when a cold layer of air basically moves into an area. And for areas like the basin, this acts as a barrier and traps emissions and causes them to pool in local areas. And the highest levels of ozone is produced during these times, especially when there's snow cover, when the sun can come and albedo from the snow and the sun is reflected and basically acts as a fuel to drive these chemical reactions. And these episodes usually end by a high pressure storm system that moves into the area and essentially flushes the basin out and moves all of the excess emissions up into the higher atmospheres. So in the 2019 season, this again is during the 27th of February, we saw something pretty interesting we weren't really expecting, and that is high alkenes near the river basin here, which is some of the lowest areas of the basin, and then primarily over the oil field. And this is concerning because alkenes have double bonds, which make them more reactive chemicals and more important precursors for the formation of ozone. In contrast to alkanes, which we see in higher composition all the way across the basin, alkanes are singly bonded hydrocarbons that are less reactive than the alkenes. So that's why we're more concerned when we see higher alkenes. And I skipped a slide. So again, we saw this in our 2020 deployment. So this was January 10th, a day collection, and we saw again high alkenes near the river basin, and then again primarily over the oil field. So we wanted to look more closely at how much alkenes we were seeing percent by mass. And if you look here at these 2 graphs, C8 and over, this represents the oil side of the field in contrast to the east side of the field, which is mostly gas wells. And we saw that there was much higher mass of alkenes on the oil side of the field. And in contrast, or also in addition to that, we looked at maximum incremental reactivity down here, which basically allows us to determine how reactive these compounds are. And we found that the alkenes on the west side of the field were dramatically more reactive than alkenes over the gas side of the field. So what type of sources are we looking at for these alkenes? To look at this, we started looking at different ratios of alkenes, and the alkene samples we collected were composed of primarily ethylene, propylene, and acetylene, which are compounds that are formed by combustion. In the oil field, the likely sources are oil field engines, combustors, and flares, and the ratios that we saw of these compounds pointed to sources similar to natural gas engines, which are frequent in oil wells without electricity. And because these oil field engines run on raw natural gas, we think that is what causes the slight difference in ratios between natural gas engines on this graph and our measurements. And there are no indexes of natural gas engines, so we are unable to compare our measurements in comparison to running or an actual natural gas index. Natural gas engines clearly produce a higher proportion or ratio of ethylene and propylene than diesel engines. So we don't feel that diesel engines are a likely source. And then vehicle emissions actually have ratios of these compounds that are much lower than both natural gas and diesel. So we don't think that they are likely sources of these emissions also. So we wanted to look closer at some combustion engines. So we found this area where there were 3 different compressor stations, and we placed a pod station on each side, and we did a deployment. And as you can see, we were a little disappointed to see that the emissions, even with the wind direction of south-southeast, were almost identical. So it didn't look like high alkenes were being emitted specifically from these sources, at least on this day. So we were generously awarded some funding by DAQ so that we can look more closely at emissions from different compressor engines. And there are 2 main types that we're going to be looking at. However, these large multi-cylinder engines have a more complete combustion, which is what we saw in the compressor stations, and these result in a much smaller emission of alkene, where in contrast we see the single cylinder lift engines. They have a partial combustion, which result in a much higher alkene emission. So we think that these are more likely the culprits that are contributing to alkene emissions in the basin. So we're looking forward to looking more closely at that. But the next steps for our team is to use the data from our pod campaign to create better models for indexes in the basin. And we will start by looking at wind speed and wind direction, and then also high split data, which aids in determining where an emission comes from, which is not always from the nearest source, but it's used for modeling data to look specifically at where it came from. And then lastly, we're going to look at PMF, or particle molecular factorization, which aids in simulating ratios of compounds and helps us to tease out possible sources. And this again will ultimately just help us build a more accurate inventory for our area in particular. Our second modeling task is going to be to evaluate satellite data of hydrocarbons, formaldehyde, and methane to determine a top-down emission inventory, which basically means to look at the total of emissions and then try to determine sources for precursor compounds, and then what's kind of happening at the base level of these emissions and the chemistry happening there. And this again is just going to help us make more accurate emissions for us to base our modeling efforts off of. And then lastly, we're going to test that by using photochemical simulations to determine whether this is helping us to make better simulations for ozone and emissions in our area. And we really couldn't have done that at all without the measurements and the samples that were taken from our pod measurements. So in summary, we see much higher alkenes on the oil side of the field in contrast to the gas side. And we're interested in understanding where these are coming from, as they are really important precursors for our wintertime ozone. And then we also would like to continue looking more closely at incomplete combustion of raw natural gas and identify specifically what sources are contributing to these emissions. And of course, as we can understand the sources and update an inventory that is more specific for our area, we will help improve our education of regulators and then industry in the area that will ultimately result in better regulation of ozone in our area.